during the time of the Babylonian captivity of the Jews. So when the book of Genesis was written, they took the best science of the day, assuming a flat earth, a dome that was separating the waters above the earth from the waters below the earth. And, water leaks through the dome every time it rains. There were, in fact, several domes. There was one for each of the planets that move in front of the stars. And they were very aware of the fact that there were these different objects, the 7 planets for which we have the 7 days of the week, the sun and the moon, and Mars and Jupiter, and Venus and Saturn and Mercury. Well, we even have Sunday and Moon Day and Saturn Day to this day. Within 100 years of when that was written, however, the ancient Greeks came to the realization that the world itself was round. Among other things, you could see the curved shadow of the round Earth on the moon when it passed between the moon and the sun during a lunar eclipse. And this idea of a round Earth was well established, from the ancient Greeks into the Middle Ages. This below here is a series of pictures of a globe that was made just before Christopher Columbus went to find the New World. And you can see it's got a pretty good description of Europe and Asia and Africa, but on the far side of the world, it's all ocean. And there was a reason they thought it was going to be all ocean. You probably are familiar with Aristotle's idea of the universe, the round Earth in the center surrounded by concentric spheres, crystalline spheres, spheres that were transparent so you could see each planet out beyond the previous planet. The center of this universe was the Earth, not because it was the most important, but because rocky material, earthy material, had a natural place in the center. And it wasn't that the Earth was a special place, it was the only place. And in fact, it was the bottom of the universe. Now, rock falls through water, so water was the layer that would go on top of the rock. Air bubbles up through water, so air is the layer that goes on top of water. And fire in the air also is seen to go upwards, so fire is the region that fills the rest of that globe below the first transparent sphere where the moon is found. What does this have to do with the idea that the Earth and the water is all gathered to one side of the Earth? Well, let's go back to the way Genesis describes it. God also said, "Let the waters that are under the heaven be gathered together in one place, and let the dry land appear," and so it was done. Now think of it. If Earth is naturally at the center and water covers the Earth, the question they had was, how do we have any dry land at all? And the answer is, God made it so. God made it so in this Aristotelian and medieval view by taking the Earth and moving it to the side of the sphere of water. So there was one portion, one dome of Earth sticking above the sphere of water, which is being held back. And of course, the Earth is spinning through the center of the sphere of water. There is just this one area of dry land, and what the heck, let's put Jerusalem at the center of it. They didn't know if that was going to be true or not. But the rest of the Earth would necessarily have to be covered with ocean. That incidentally gives rise to the idea of the high seas, because when you're getting on a boat, you're actually sailing uphill compared to what the sphere of rock ought to be. Now, these pictures are the pictures that Chris Graney put together for me. But in fact, you can also find this image in books, well, this dating from 1663, which is 30 years after Galileo's book, by the way. And there's the earth, dry earth, the earth there with cracks through the earth and water that can travel from the dry earth through these cracks to the big ocean on the far side. This picture wasn't just something from the Middle Ages. You can find it described in a sermon given in 1700. We're talking now after Newton had published his work, where the sermon says that the sea is higher than the earth is what men of good sound reason lay down for certain truth, and consequently it would overlay all the land if it were not held back by an almighty hand. And if you think that's 1700, 1777 in Glasgow. We're talking now more than 150 years after Galileo. The being of the vast sea, where there is such abundance of waters as some think higher than the earth, which yet are bounded and restrained from overflowing and drowning the land and its inhabitants, as once they did, remember the great flood, when their limits were for a while removed. Is that such a crazy idea? Have you ever actually looked at a globe of the earth? Most of the land can be fit into one side, even with the New World. And in fact, if you look at such a globe, you find that, okay, the Americas are sort of lying along the edge there, but the center, the actual mathematical center of where all the landmass is not all that far from Jerusalem, as it turns out. This image was part of the medieval way and even into the early modern way of picturing how the world worked. And to be honest, it's almost correct. A wonderful book on astronomy from the 1700s was written by Johann Bode. And in a footnote, he describes how the positions of the planets around the sun, by this time he's accepted the Copernican system, how those positions can be described using a simple mathematical formula, a formula that actually he had stolen from a fellow named Titius, who he doesn't give credit to. And the formula goes like this. Let's take Mercury and give its distance from the sun a value of 4, because it's actually 0.4 times the distance of the Earth to the sun. So the Earth's distance is going to be 10 in this system. If you add 3 to that number, arbitrarily 3, you get the position of Venus, 0.7. If you add 3 to that, you get 10. If you add twice 3, which is 6, you get Mars. If you add twice 6, which is 12, well, there was no planet seen there, but knowing that it ought to be there, people started looking, and in the year 1800, on New Year's Day, Piazzi, a priest in Sicily, actually discovered Ceres, the first of what we call the asteroid belt. So we were going from 16 to 28, that was 12, double 12, and you get to 52, which is where Jupiter is. So double 12 is 24, double 24, you add 48 to that, and you get to where Saturn is, and you double 48 to that, and you even get 96, where Uranus is. Uranus was basically discovered at about this time. This pattern worked so beautifully that people assumed this must be telling us something fundamental about where the planets are placed. So in the middle of the 19th century, after this law was well established, Neptune was found, and they applied Bode's law to Neptune, and guess what? It doesn't work at all. Not at all, at all, at all. Oh well. It didn't stop people from assuming that the law could exist. They just sort of didn't understand why the law existed in the first place and why it shouldn't work for Neptune. But, in 1932, they found Pluto, and Pluto fit the law. So it proves that Pluto must be a planet, right? No. It's a great idea. It's almost correct. Planets do have to be spaced out from each other, or else their mutual gravity is going to cause them to shift around and become unstable. But if you actually look at the numbers really aren't all that good. They're only good about 5 or 10%. So for it being a rigid law, it's not all that rigid, and you do have the problem of Neptune, which just doesn't fit the law at all. But there's an even worse problem. In 2006, people with very fast computers started modeling how planets were formed. And here we've got a computer model showing the motions of Jupiter, Saturn, Neptune, and Uranus, and then a body of smaller objects out beyond Uranus that hadn't quite yet formed themselves into a planet. All during this time, Jupiter is ejecting asteroids from the asteroid belt. 99.99% of the asteroid belt is ejected. But as these things get moved out, Jupiter's orbit shrinks a little bit until it becomes in resonance with Saturn. Saturn then moves to become in resonance with Neptune and Uranus. Neptune jumps outside of Uranus's orbit, and everything else is scattered. And it turns out this kind of scattering and shuffling of the positions of planets is the rule, not the exception. Bode's law shouldn't work because where the planets are now is not where the planets were formed. Now, back when Bode was, coming up with that law, he didn't know that. Back when I was a student 40-odd years ago, the only solar system we had to study was our own solar system. And when you looked at it, you noticed a couple of interesting patterns. For one thing, all of the rocky planets are small and close to the sun, and all of the gas giant planets are big and far away from the sun. Why would that be? Well, we had a perfectly reasonable explanation. The sun and all the planets are being formed out of a cloud of gas and dust. We assumed that then. We have since discovered many of these gas disks, so we know that that's happening. If they're formed in a cloud of gas and dust, the gas and dust closest to the star being formed is going to be the hottest. Now, what's the most common material in a star? Hydrogen, and after that, helium, and after that, oxygen. If you're far enough away from the star, the oxygen and the hydrogen can combine to form water. And if you're even farther away from the star, that water is going to freeze into ice. Now, the dust is slowly accumulated into little planetesimals that grow into planets. But if you've got ice, which is far more abundant than everything else combined, then you've got a lot more stuff to accumulate. So once you get beyond the ice line, the frost line there, the planets are going to grow much faster. They're going to grow so fast that they're going to begin to collect the gas from the nebula on top of the icy cores. This explains why you've got the gas giant planets outside the ice line and just rocky planets in the inside. But it explains something else. Really great if you could explain more than one thing at a time. It explains why the rocky planets are so small and the gas giants are so big. The biggest rocky planet is Earth. Obviously wasn't big enough to hold on to a lot of gas. But as soon as you got a core that was big enough to hold on to a lot of gas, then it would leap in size because it would gather all the mass of that gas onto the planet. So you would expect that there might be rocky planets Earth size or smaller, gas giants Neptune size or bigger, but there should be a gap in the size of planets. There shouldn't be anything between rocky Earths and gaseous or icy Neptunes. Then we began to discover other solar systems. We've got more than 4,000 solar systems that we've discovered now, where we can map out the planets and where they orbit and how big they are just by seeing how much they block out starlight as they pass between the star and us. The first thing you discover is that the big gaseous planets can be found anywhere. Our solar system is unique in having all the rocky planets close by and all the gas giant planets far out. And does this uniqueness have something to do with the fact that there's life on our Earth? We don't know. Really good question. But the other thing that's embarrassing is that the vast majority of the planets we have discovered are right in that gap that our theory said was supposed to have no planets at all. Oh well, our theory was almost correct. I've got my own story about getting things almost correct. It starts with Harry Potter. Maybe you remember in the Harry Potter books, Harry's taking an astronomy class and he's, writing up his astronomy homework, and Hermione, the know-it-all, is looking over his shoulder. And she goes, "Harry, the moons of Jupiter are covered in ice, not mice." I'm reading this and I'm going, moons of Jupiter covered in ice. That was my master's thesis at MIT about the icy moons of Jupiter. And, that was me at MIT back in the 70s. Forgive the hairstyle. What I had actually done, I wasn't the one who proved that there was ice. I was the one who explained why there was ice. I did a computer model that showed that if you had a moon that was a mixture of rock and ice, there was enough heat generated in the rock to cause the ice to melt and flow to the surface. Nice bit of calculation. But here's the question. I did this work starting in the 1970s, 1972, 73. I remember writing the computer programs while watching the Watergate hearings on TV. How did I know that the moons of Jupiter were a mixture of rock and ice? We hadn't had spacecraft go there yet. Voyager wouldn't get there till 79. Even Pioneer didn't get there till 75. We didn't even have spectra in our telescopes that showed that ice was there, not until 71, 72. But we already knew that they were a mixture of rock and ice. How did we know that? Well, there were two bits of information you could get out of a telescope that would strongly suggest rock and ice. The first was that, Europa is a really shiny place. Europa and the moon are about the same size, but the moon only reflects 12% of the light that hits it, even though it's covered with a lot of rock that's pretty white colored. Europa reflects 64% of the light that hits it. Not many things in nature are that bright, and especially not many things that are common in nature. But one of the most common things in nature, as we talked about, was water ice. And water ice is very shiny. Ask anybody who has to wear, sunglasses when they go skiing. The other thing is the density of the moons. The density of rock is about 3 times the density of water. These moons were much lower than the density. Okay. If the brightness and the density both tell you that water ice is common, who was the first guy to figure that out? When did we know the intrinsic brightness of these moons? When did we know the density of these moons? Well, density is the mass divided by the volume. How do you measure the mass of something? In space, you have to have something orbiting next to it to measure it easily. I could give you the mass of the sun because we've got Kepler's laws that show that the mass of the sun tells you how fast the planets are moving around the sun. We knew the mass of Jupiter because Jupiter's got moons. The mass of Jupiter tells you how fast the moons are moving around Jupiter. But there's nothing in orbit around the moons. How do you get the mass of the moon? A fellow named Laplace was able to do this through some really heavy-duty mathematics, looking at how the various moons perturbed each other. And he did this in 1803. And he was able to work out the relative masses of the moons to a pretty good decision, about 10% of, within 10% of what we think now. Callisto's a little bit further off. But certainly Europa within 10%. Now, of course, he was measuring the mass relative to the mass of Jupiter, but we knew the mass of Jupiter because we knew how fast the moons were moving around Jupiter. Of course, to actually get the mass of Jupiter, you have to apply Newton's law, and Newton's law has this gravitational constant, big G, but Cavendish had measured big G in 1795. So by 1803, we actually knew the masses in kilograms of the moons. How do you determine how big the moons are? That's trickier. What you can measure, though, is how long it takes for one moon to move in front of another or to move into the shadow of Jupiter. You can time that to a high precision, and you know how fast they're moving, and you know how far away Jupiter is, so you can work out how big the moons are. By the 1840s, we knew that. And that gives us both the volume of the moon and the mass of the moon, so you could calculate the density. It also tells you something about how intrinsically bright they are. You know how bright Jupiter is, and you know how big Jupiter is, and you know how bright these moons are compared to Jupiter. You can judge that just with the naked eye. The naked eye is really good at judging the brightness of things, or you can compare these against standard stars. But are the moons small and shiny or big and dim? Once you know the size of the moon, then you can solve the tall, small, or big. And then you can work back what's the intrinsic brightness you need to get the shininess that you actually see in the telescope. So all of this was known by the middle of the 19th century. Go to some popular books by really good astronomers and look up, and you will find tables of the moons of Jupiter and their masses and their sizes, but you also find other things. This is a couple of the books that I looked at. I actually looked at a bunch of them. But in particular, I want to quote the bigger book first, which is by Simon Newcomb, who was the great astronomer of his era. And he writes, the light of these satellites, the moons of Jupiter, vary to an extent which is difficult to account for except by supposing very violent changes going on. And I'm reading this and I'm going, the brightness, the intrinsic brightness changes in a way that's hard to predict? I wrote a thesis about these moons. I never heard that. I've looked at them in my telescope since I had a telescope when I was a kid. I've never noticed that. But it turns out he's not the only one to say that. There's a whole literature going back into the 1700s of people discovering wild changes in the brightness of the moons of Jupiter. The best explanation seemed to be either they were physically changing their shape, or maybe they were spinning really fast to the point where they looked like pancakes, and sometimes we were seeing them flat on and sometimes we were seeing them edge on, but they were tumbling as they spun. Really weird. The other thing that was odd in this wonderful book is that he gives you a table of the sizes and the masses, but he never divides the one into the other to give you a density. Nobody divides the one into the other to give you a density, because in those days that was a question that nobody asked. They weren't interested in what stars or planets were made out of. That was astrophysics. That would come much later. They were only measuring where the stars and planets were. The one exception is a fellow named George Chambers in a book in 1861 where there's his table and there's, the masses and the radii, and he divides them to give densities relative to the density of water. And then he looks. Well, look at the densities. 0.1 times the density of water. I mean, rock is 3 times the density of water. Water is 1 times the density of water. Ice is 0.9. Air is, 1,000th. But there isn't anything in nature that's only 0.1. Even balsa wood is denser than that. He never bothered to look at those numbers and figure out what does this mean. In fact, he never bothered to look at those numbers and say, did I get those right? Because if I take his masses, which aren't all that wrong, and his volumes, which aren't all that wrong, I get totally different numbers than he gets. The numbers I get are actually pretty reasonable, a little bit more dense than ice because it's a mixture of rock and ice. His numbers are not only wrong, they're not even consistently wrong. They range anywhere from 10 times out of bounds to only 5 times out of bounds. I have no idea how he made those mistakes. So who finally got it right? A fellow named Pickering, working at the Harvard College Observatory. That's the Harvard College Observatory in 1900. That building that you see there was where my office was in 1980, so we're talking a third of the way back in time from when that picture was taken. And around 1900, he publishes a table, and the table has wonderful densities based on 2 different estimates of the size and the mass. And he also comes up with an albedo, how intrinsically bright they are. His albedos are about a factor of 2 low from what we know now, but they're not bad. They're pretty bright. And he writes, it's long been thought that the lights of the Saturns of Jupiter were variable. This is not viewed or sustained by the present measurements. What this guy did was he invented a gizmo that would have the moon in one side of his eyepiece and then Jupiter separated in a different side of the eyepiece with a set of filters that he could adjust to make them brighter or dimmer, and he would dim down Jupiter until it matched the brightness of the moon. Doing that, he shows that the moons are constant brightness. And in the process, he makes me realize what had gone wrong with all of the other observations. if you're trying to guess the brightness of a moon of Jupiter, when Jupiter itself is also in the field of view. Jupiter is almighty bright, which causes your iris in your eye to squinch down, which will make the moons look dimmer. And then you look to a standard star and your eye pops right back up and you can see fainter things. Nobody before him had figured that out. Finally, Pickering worked it out. He then points out the densities are much lower than the density of the moon. Such figures imply that these bodies are either enveloped in clouds, which is not likely because how could they hold onto an atmosphere, or they're like a swarm of meteorites. The density and brightness are what we would expect if they were composed of loose heaps of white sand. So close! But he says white sand rather than ice. Why does he think that they had to be a swarm of meteorites? Why did he think that they had to be something loose? Because it's impossible to understand how a rigid body could have all the varying shapes that were required by the changing brightness that he had already just shown didn't happen. Almost correct. It was not until Jeffreys in 1923 that he works out that the densities of the moons are comparable to the density of ice. And even there he's only partly correct because he wants to use this fact to argue that Jupiter and Saturn, which have similar densities, are themselves also made of ice. I don't think so. But by the time I wrote my thesis, I knew that they were made of ice. I knew, in fact, that the ice could melt. And at the end of my thesis, the very last paragraph I write, given the temperature of the interiors, and especially the silicate layers through which the water is going to be percolating, the possibility exists of organic chemistry. You either got the organic chemistry from methane in the ice or carbon in the rocks. And then I conclude, we stop short of postulating life forms in these mantles, leave such to others more experienced than ourselves in such speculations. I was thinking of course, Carl Sagan, who was famous for speculating life. I presented my work on the icy moons at a meeting at the University of Arizona in 1975, the very first meeting I ever gave a paper, and the chair of the session was Carl Sagan. And before my talk, I go, Carl, what about the idea that there's life in these mantles? And Carl goes, life needs energy to live. The energy comes from the sun. If you've got an ocean underneath a thick crust of ice, it's going to be very dark. There can't be life there. And I go, oh, geez, all right. So I never talked about it. 3 years later, we discover at the bottom of the ocean, volcanoes giving off hot gases, which give off energy that is used by life forms, even though it's really, really, really dark there. And inspired by that, a group of people take my science fiction idea and do real science on it, showing that Europa might be habitable. Incidentally, Steve Squires, the second author there, was Carl Sagan's grad student. The moral of this story is this. Science makes mistakes, but it also corrects itself. And these mistakes are important. You know, if Dr. Smith makes a mistake and Dr. Jones can point it out and fix it, that mistake is what motivated Dr. Jones to do the work in the first place. If you're going to do science justice, you have to glory in its mistakes. A good mistake is a new idea that's reasonable, pushes your understanding deeper, an idea that's almost correct, but a wrong, a mistake, but a mistake that can be tested and found wanting in interesting ways. Science is always going to be found wanting. A science that's perfect is a science that's dead. But also, the mistakes are often not in your data, they're in your imagination. Imagine, if you will, that you're an intelligent tuna swimming in the ocean. You would have no idea that there was a sun outside of that thick icy crust that you're swimming underneath. You would have no idea that there was a Jupiter there. You would have no idea that the universe was any bigger than the ocean you could swim in. Until maybe, one day, a giant impact pokes a hole in that ocean, you get swept up, and finally see the universe, and it's full of stars. Because you can look through the crystalline sphere that made your universe. Thanks a whole lot. Um, One of the advantages of having a recorded talk like that is that I can hear all the mistakes I made, and there are two or three. We'll see if we can find them. But we'll let the people here running things chat to you, and then we'll have some questions.
Thank you, Brother Guy. Well, good evening, everyone. I'm Walter Iwanenko. I'm the Provost and Vice President of Student Experience at Gannon University. Welcome to all of you for joining us on Zoom, our Gannon family, our friends, our alumni. We're so glad you're able to be with us. I want to first give a hello from President Dr. Keith Taylor. He'd love to be here to greet you personally. He looks forward to this event very much, but unfortunately, he's not able to be with us this evening. We're honored to have a group of students with us here in the Yale Ballroom this evening. And we're also here, we want to acknowledge two very special guests. Bishop Lawrence Persico, Bishop of Erie and the chair of Gannon University trustees. Mr. Tom Loftus, a former trustee, who with his wife, Mary Christine, established the Loftus Lecture for Catholic Thought and Action over 10 years ago. Thank you, Bishop and Tom, for being with us in person on the Erie campus tonight. And now I have the privilege of formally introducing our honored speaker, Brother Guy Consolmagno, of the Society of Jesus, the director of the Vatican Observatory. Hello, Brother Guy. It's good to see you in front of me here. I hope you can sit tight when I give your introduction. Your resume is quite impressive. So I hope you forgive me for giving a short summary because I know people really want to hear from you more than me this evening. Guy Consolmagno is a native of Detroit and studied planetary science at the Massachusetts Institute of Technology and the University of Arizona, and then did his postdoctoral teaching and research at MIT. He left MIT to serve in the Peace Corps for 2 years teaching in Kenya. Upon his return, he continued to teach physics before joining the Society of Jesus, more commonly known as the Jesuits, taking his vows in 1991. He was assigned to the Vatican Observatory in 1993 and was named by Pope Francis as the director in 2015. Brother Guy is a world-renowned astronomer whose research interests focus on meteorites and asteroids. His writing continues to contribute to the field of scholarly research in physics and astronomy, as well as making science accessible to a wider audience, including his book, Would You Baptize an Extraterrestrial?, which he co-authored with fellow Jesuit Paul Mueller in 2014. He has held distinguished professorships, given countless lectures, serves on boards and learned scientific societies, collected and analyzed meteorite samples in Antarctica, and can boast of an asteroid named in his honor, number 4597 Consolmagno. Gannon University is honored to welcome for the spring 2021 Loftus Lecture, Brother Guy.
Thank you, thank you. So as I say, I listening to that talk, I heard at least two different places where I misspoke. It's not that the Earth was pushed through the water; it's that the water is held back from the Earth, and that wonderful image of the world that was, different layers, different crystalline layers. And I think my description of how you calculate Bode's law, though it works, there's a simpler way of doing it, which is actually in the footnote if you were reading along. Basically, if you ever look at this thing, what's on the screen is more correct than what I'm saying, because my talk was almost correct. I'd be delighted to hear questions or reactions or people just wanting to know what was that all about? Or could I explain something a little more clearly or give some more examples of things that were almost correct? The great advantage of having a recorded talk was that it kept me from going on forever because I could talk about this stuff for hours.
Hi, my name is Elizabeth Schumacher. I'm a mechanical engineering student. Um, my question is, in the demonstrations that you had that showed orbits of planets around the sun, and in the the video of the moons orbiting Jupiter, they all seem to orbit in the same direction. Is there a reason for that?
We think there's a reason for that. There's actually a couple of exceptions, which are fascinating because then you can test whether the reason works. If you start with a ball of gas that's spinning, that has an intrinsic spin, and you collapse it, the angular momentum is going to be in a particular direction. And that means that the star should be spinning even as the stuff goes in, the star will be spinning faster. The gas cloud should be spinning. Any whirlpool that is set up in that gas cloud should also have the same angular momentum. And that works for the most part in our solar system. The sun is rotating in the same direction that the planets are going around the sun, in the same direction that the moons are going around the planets, with a couple of exceptions. Venus is very, very slowly spinning backwards. Well, you can wave your hands to figure out maybe it was, it's the interference with gravity of other nearby planets. Uranus is spinning on its side, tilted over sideways. Well, if the moon was formed by a giant impact of something the third the size of the Earth hitting the Earth, and if Uranus had something that really big that caused it to, about that size, hitting it off center, you could explain Uranus being tilted over sideways. The largest moon of Neptune is going around backwards. And there are some very tiny moons of the other icy gas giants, which tend to go around retrograde. That's what you would expect for bodies that were captured rather than formed in place. But you notice the problem we've got, that it's like Bode's law. It works except when it doesn't. And you can use the patterns you see to try to test whether this theory is general or not. But when you see exceptions, you're either forced to try to come up with a reasonable explanation for why they're exceptions, but you also have in the back of your head, maybe this is just one of those theories that's only almost correct. At the moment, we can't tell from other solar systems. All we can tell is that the light of the star dims and then brightens up again. But you can't tell intrinsically which way the planets are moving just from the light dimming. So we're going to need better observations to see if this pattern holds true for all the other solar systems. But there's no reason to think that it doesn't.
Thank you.
Good evening, brother guy. My name is Danielle Kowalski. I'm an interdisciplinary major. I was wondering, why did you want to do astronomy, especially at the Vatican, and when you could have done it anywhere else?
I didn't want to do astronomy. I had this research career, and I was kind of fed up with research because it was a lot of money grubbing and competition, and I didn't like the culture of it. So that's why I joined the Peace Corps. Plus there was this, why am I doing astronomy when people are starving in the world? Good heavens, what a waste of life. Well, the first lesson I got being in the Peace Corps was that the people who I met in Africa wanted to hear about astronomy. They wanted to look through my little telescope. This telescope is the one I took with me to the Peace Corps. And everybody in the villages in the most remote part of the country would, stand in line to see the rings of Saturn through the telescope because it's really cool. And it gets you to ask questions about who you are and how you fit in and what this universe is all about. And asking these questions is what makes us more than just well-fed cows, because we don't live by bread alone. It's literally true. We have to feed the questions of our souls. Well, that got me into teaching physics, and that was great fun. So I thought if I joined the Jesuits, I could teach and then I'd be standing for something bigger than just my own career. But you take 3 vows as a Jesuit, poverty, well, I'd been a grad student, I was used to that. And chastity, well, I've been a grad student, I was used to that. But obedience was the tough one. Under obedience, they ordered me to go to the Vatican Observatory. They didn't ask, they told me. And so I had to live in this papal palace and eat that terrible Italian food and look at that, terrible Italian scenery. And oh yeah, do whatever science I wanted to do with no time limit, no idea that I had to get a grant. And if I didn't have a result after 3 years, the grant would expire, no tenure. I could do long-term projects and I could do them for the glory of finding the truth, not for my own career, not for my own reputation. And it has been an eye-opener. It reminds me of why we do science, why I wanted to do science in the first place, why I found joy in that science. And where you find joy is where you find God.
Thank you.
Brother Guy, we have a question from the folks on Zoom who are remote. Here is the question from Greg Badak. We're interested in your thoughts on Perseverance's landing on Mars. What do you hope it might find there?
Perseverance is a fantastic mission in a long string of fantastic missions. And part of the genius is not just the engineering that went into that one mission, which is great, but that it is part of a 25-year series of missions that were carefully planned out, each one to discover things that then inspired the instruments that go on to the next mission. Back in 1976, we sent the Viking lander to Mars, which, we're going to look for life. And so they had 3 experiments on the Viking lander, and 2 of them said probably not, and the third one was ambiguous. And after we landed, we realized we'd probably flown the wrong instruments. What's important to Perseverance is that it is a spot in a carefully thought out sequence. And what I hope it discovers is something that we didn't even know to look for, because that's what's exciting. Science is not getting the answers in the back of the book. Science is finding out that the world is just a little more complicated than what the answers in the back of the book might tell you. That's what makes science fun. That's what gets you up in the morning to be excited about it, to want to go and spend the years that it takes to build an instrument, to build a spacecraft like that.
Hi, my name's Tim Caulfield. I'm a finance major here at Gannon. My question was, when you looked at those large gaseous bodies and then the small rocky bodies, and then you said in other solar systems, it didn't seem to follow the rule that there had to be a gap between the size. I may have missed it if you said it, but did you have a theory as to why those bodies had that intermediate size?
The best explanation is that our previous explanation was too simple. It was too glib. That gas giant planets are not just icy cores that capture gas if they happen to be around at the right time, but that planets form in a more complicated way, that they can be spaced out in time, and that just as we've seen with that model I was calling the Nice model, it comes from a bunch of scientists in Nice, France, that the planets get shuffled, and in the shuffling, they can also interfere with each other, collide with each other, break each other apart, or gather together. In other words, the simple picture that we had was incomplete. It's not that it was wrong, it was incomplete. And I think there's a lesson there for us as people of faith, that the things that we were taught as children about our faith. That's not wrong, but it's incomplete. That the real world is messier than that. The real world has all of those elements, but then when you try to actually live the real world, you discover it's not so easy and you're going to make mistakes. And that's part of life. And then you have to learn how to recover from the mistakes and then say, okay, how could I, combine these two different things that I thought were going to be true into something more complicated than what I thought.
I have a quick follow-up to that. So
Mhm.
those bodies that you found in other solar systems, could you tell if they were gaseous or if they were rocky?
In some cases you can, but for the most part you can't. Um, the way if the question is the mass, if you see them passing in front of the star, you see how much light they're blocking. That tells you the volume. But how do you know the mass? If you can also observe them pulling on the star as they move about, then you can work out the mass of the planet. And in some cases, they look to be super Earths. They're much bigger than Earth, but still rocky. That's basically only a fraction, maybe 10% of the planets we've seen so far that we can make that calculation. So it comes in a wide variety, a wide range of things. There are some, sizes where you don't know, is it rocky, small rocky with a bit of gas around it, or are they giant balls of ice? We're now recognizing that Uranus and Neptune are different from Saturn and Jupiter in that they are really large ice balls with a little bit of gas on top of them.
Thank you.
Hello, my name is Noah Marangoni, and I'm a psychology major. And one of the things that I've been hearing, so you mentioned that there was this notion that Earth was the center of the universe because that's where Earth had to go. It was the densest. And I've heard in relation to that humanity was thus at the sump, or like the lowest moral point of the universe as well. And like
It's at the bottom of
whenever,
the universe rather than the center of the universe. Exactly.
yeah, and like whenever we discovered that wasn't the case, that elevated humanity, like I guess my question is like, what are your thoughts on just that notion of us being at the bottom in morality
Yeah.
as well?
It really didn't elevate humanity. What it did is it lowered everything else in the physical universe down to our level. One of the ways you could tell that we were inferior to the other planets was that the planets seem to move forever, but things on Earth, they slow down and they stop and they wear out. Now we know that everything in the universe slows down and stops and wears out in the physical universe. So it didn't promote us. It basically showed that anything in the physical universe that we can see that is created, we are assuming obeys the same laws of physics and the same laws of chemistry.
Thank you.
Hello, brother guy. My name is Dominic Ellis. I'm a mathematics major. And do you think with the discovery of other parts of the universe and different things outside of Earth, that there comes these bigger jumps in mathematics as well?
Ooh, the philosophy of mathematics is a really, really tricky area that I'm only aware of and I don't practice myself. We had a mathematician living in our community for many years, Andy Whitman, who was a master of Lie algebra, which of course is spelled Lie. So we always said that everything he did was a lie. But the question that he would pose to us is mathematics discovered or invented? And it's a wonderful question because it doesn't have an answer, but it makes you think about what are we doing when we do mathematics, which then leads to what are we doing when we're doing science? How much of our idea of physical laws are describing what the universe does versus us imposing our expectations on the universe? And the answer is it's a bit of both. And that's one of the things that I wanted to get across in this talk is that the universe is real and our science works, but don't get too full of yourself because our science works to a point. And yet part of the way the science works is by us seeing what we expect to see. And that means that science, though I love science, it's my life. It's why I got the MIT ring here. But science is not something that I'm going to base my life on the way that I would base my life on the love of God. And so if I can go a little bit off from this, the great thing about science is we have explanations that we can understand because the explanations were invented by human beings. So what one human being invents, another human being in theory might be able to understand. But they are only approximations of the truth. They're only almost correct. Science is understanding, seeking truth. In our faith, we have things that we know are true, like God loves me. But they're truths that we don't totally understand. It's truth-seeking understanding where science is understanding, seeking truth. You can see why they're very closely related and why they can help each other out, but one is never the substitute for the other.
Thank you.
Brother Guy, we have another question that came in from Zoom. Do you have any hunches or suspicions about current astronomical or cosmological theories that you think will turn out to be almost true?
Well, in the last 20 years, we've understood that most of the universe is something that we don't know what it is, but we've got a name for it, dark energy. And for the last 50 years, we were aware that there's matter which is causing galaxies to behave in a funny way when we don't know what it is, and we're calling it dark matter. I hope in 100 years' time, we will be able to look back and say how foolish we were, because now we know in much better detail what these things are. And so the thing that's wrong is not that there's stuff we don't understand that we've given labels to, but to say that it's only everything we're lumping together as dark energy. Maybe lots of different things going on, and we don't even have a clue as to what those things could be yet. I think that our understanding of how planets are formed is just a little incomplete. And we will never be able to understand that until we really know other solar systems better and we can begin to find commonalities there. I'll throw this in a different way to react to a question that some people might have, but maybe they don't want to ask. But it reminds me of this question that I get a lot, which is, oh, you're a Jesuit brother and you're also a scientist. Do you ever come up cross with something where your religion says one thing and your science says another, which do you believe? Because that doesn't happen. They're not talking about the same things. But what happens all the time is this bit of science disagrees with that bit of science. And that's when you get excited. Because that's when you learn that there's something new to be learned that you didn't know you didn't know. And if nothing else, it means I'm going to get a paper, because, wow, I've seen something that I hadn't noticed before. So finding these contradictions, finding that you're wrong, is one of the most exciting things that can happen. I'm reminded of a statement that Isaac Asimov wrote once, who was a science fiction writer, but also a very good science popularizer. This is very true. He says, the most exciting thing you hear in a laboratory is not, Eureka, I've discovered. The most exciting thing you hear in a laboratory is, huh, that's funny.
Brother Guy, Father Chris Singer from the Diocese of Erie. And just building on what you were just saying, and you said repeatedly this evening how exciting science can be in general and how exciting it is to you personally. And you mentioned to us in your talk that in the 70s, you studied and wrote about the moons of Jupiter. trying to draw conclusions about them. Well, now in a couple of years, NASA intends to send the Europa Clipper mission to one of those moons. And I'm curious, what are you most excited to learn about Europa? Having thought about that moon and its sister moons for many years, what are you most excited to learn about from that close-up mission that's upcoming?
I have to confess, what excites me is what excites everybody else. What I wrote about in my thesis in a very snide 21-year-old's way of, we leave that speculation to other people. Yeah, right. I was speculating like mad because I got into science by reading science fiction. I want to know, are there intelligent tunas or even, unintelligent amoebas living in those oceans? And apparently there's enough water that leaks out of Europa, and certainly we see geysers of water leaping out of another moon, Enceladus, that if we could capture some of that material and look for highly evolved organic chemicals, even maybe other kinds of life form. That, I think of all the places in our solar system, those are the places most likely to have life alive even today. And to be able to find that would be really exciting, because just as we know so much more about solar systems now that we've got more than one to look at, we would understand so much more about what life is once we have more than one example of life to look at.
Thank you.
I also have to say, in 1975, I never thought I'd live to see the day that spacecraft would go there and actually test some of these ideas.
Brother Guy, we have another Zoom question. What is the role of gravity in the formation of life? And are there any other planets with the same gravity in this or other universes as Earth?
Well, can't speak about other universes. I assume he means other galaxies or other solar systems. And the answer is we don't know. There are some places we've been able to find that are not that different from Earth, but our techniques for discovering planets aren't quite good enough to see Earths yet. We can see super Earths, things that are 3 to 5 to 10 times bigger than Earth. But, as our techniques get better, eventually we'll be able to see Earths themselves. The answer is we don't know. We don't know what is essential for life and what is an accident. That's one of the reasons we want to find life elsewhere, because we don't really know exactly how life arose on Earth. We can put some limits on it. We can tell you when it happened. We can tell you the kind of conditions that were around when it happened. But, does the fact that the Earth have a moon and therefore big tides and oceans, is that essential for the creation of life? Maybe, but we don't know. Is the fact that the solar system was stable enough that we didn't get all mixed up with gas giants whizzing past us mean that there were all sorts of giant impacts that killed off life the way the dinosaurs were killed off? Is that essential for life on a planet? We don't know. And the glorious thing is that we now know that we don't know. But even to find life in, an ocean of icy satellite, or to find fossil life that maybe used to exist on Mars, or maybe still exists below the surface of Mars where the UV light doesn't kill it, that would be exciting. But to also find that there isn't life there would be telling. To be able to definitively say, if it's there, it's hiding really well. That would tell us something as well.
Brother Guy, I'm Kevin Richardson, and I'm a philosophy major. My question to you is, what is your vocation story, and why did you become a Jesuit priest?
I didn't become a Jesuit priest. I became a Jesuit brother.
Oh.
All right. Let me tell you the vocation story. This is one of these that I love telling because it's such a goofy story. Went to the Jesuit high school. And of course, I was growing up as a kid in the space age, and I was space crazy, of course. And then I went to the Jesuit high school, and they said, all the smart kids do Latin and Greek. So I wanted to be a smart kid, so I did Latin and Greek. And I graduated with no idea what I wanted to do. So I went off originally to a certain college run by the Jesuits in Boston, whose name I won't mention. And what I discovered is that most everybody in the guys' freshman dorm were more interested in drinking than anything else. The local liquor store would deliver to the freshman dorms. You didn't even have to go out and get the stuff. It was against the law, but that didn't seem to stop them. And then after the obvious result happened, and they'd get sick in the hallways, and the smell was going to permeate the place, and then they'd start flunking their classes. And I couldn't stand the smell of this stuff, and I tried, drinking, and it just tasted awful, and it was expensive, and you could use that same money to buy chocolate. What was the point? I didn't get it. So as the kids were failing their classes and making my dorm unlivable, then they'd see me as somebody who was doing okay, and they'd pour out their troubles to me. And I'm thinking, why are you telling me your troubles? What do you expect me to do? Life is tough, and it's especially tough when you're stupid. Good grief. So in order to get away from all the idiots in my freshman dorm, I thought I'd join the Jesuits. So I went and found a Jesuit. And he said to me, son, I hate it when they call you son, have you prayed about this? Going, I'm 18 years old. Who prays? Geez. I guess if you're going to be a Jesuit priest, my girlfriend from high school had dumped me, so I figured I had no future there. What the heck? But I went to my room, closed the door, sat on the floor, and said, well, here I am, God. I'm trying to get out of the dorms, and I'm miserable here. And they said I'm supposed to pray. Do you need a vocation? I know they're desperate vocations. They'll take anybody, right? I don't know what I'm waiting for, but I'm, voice from the ceiling. Voice from the ceiling didn't come. Nothing came. And I got to feel really stupid. And then this question popped in the back of my head, you're going to be a priest, right? What does a priest do for a living? Their day-to-day job. I know what they do on Sunday. They tell everybody else how to live. I could do that, yeah. But the rest of the week, I guess they have desks, right? You work, you have a desk. I guess there's papers on that desk. What are those papers about? They're about people. People with problems. People just like the jerks I'm trying to get away from because I'm terrible at dealing with people with problems. Boy, this would be the worst job in the world for me. At which point I said, either I haven't heard anything from God because there's no God, in which case it would be stupid to be a priest, or I just heard from God that it would be stupid for me to be a priest. So that's how I didn't become a priest. Instead, I was hanging out with my best friend from high school who was at MIT, and they had the world's largest collection of science fiction and weekend movies and, tunnels you could explore and cool things going. So I transferred to MIT. I claimed I was going to be a science journalist, but I found out journalism is really hard and science is easy by comparison. And I really liked the stuff. I was really happy. I was discovering something that's called, Jesuit spirituality. God speaks to your deepest desires. I had no idea that was, God wants you to be happy. Never occurred to me that God wanted me to be happy. I just found that doing the stuff there that I was happy about. Well, when I came back from the Peace Corps and I was teaching, once again, I was happy. I loved teaching. And this is another thing I learned about, that later on, this is called Jesuit spirituality. When you're making the big decisions in your life, you don't make those decisions when life is miserable, because then you're likely to make stupid decisions like, transfer to MIT. How did I know it's going to turn out to be the right thing? You make the important decisions in life when things are good, when things are solid. And now you can tell yourself, okay, this works. What can I do to build on this? And you find the place where God makes you happy, not happy for a moment that, gives you a hangover the next day, but satisfied, but content, but that feeling of, yeah, this is where I belong. I could see myself doing this for a while. And When I joined the Jesuits at the ripe age of 37, once again, just like going to MIT, I discovered this was the right place for me, that this was where I belonged. And it wasn't for everybody. About half the people who enter religious life do it long enough to realize, no, don't think so. It's great, wonderful, but it's like dating somebody. You're not going to marry the first person you date. Actually, I know somebody who did, but most of the time that doesn't happen because you find a wonderful person, really smart, not for me. And that's fine. You're all better off learning that. And the sooner the better. So that kind of waiting for that sense of rightness only happens if you keep trying different things until you connect with that sense of rightness. And then you say, okay, I found this. Now what can I do next?
Thank you.
Incidentally, just because people are miserable doesn't mean they're stupid. It took me about 30 years to figure that one out too.
Hi, brother guy. My name's Nathan Bly. I'm an English major here at Gannon. And I have a question for you. Do you think the Bible's creation stories are more, I guess, fortified by the Big Bang theories or the creation theories of the universe?
There is this really great temptation to say, Big Bang says a burst of energy, and God said, let there be light. That must be the same thing. And then you start trying to force the rest of your science into whatever words you find in the other days of Genesis, and it doesn't work. What's more, it's totally misreading the important thing that Genesis is telling us. Genesis chapter 1 is foundational for the fact that we can do science. Let me tell you what I mean. If you do any kind of biblical scholarship, you realize that the Babylonians had this creation myth, which looks an awful lot like the creation story in Genesis. And you go, they just copied it. No, they took the best science of the day. We know that Genesis was probably written during the Babylonian captivity because it's got Babylonian words in the Hebrew. The word for chaos is the Babylonian word for the name of the dragon that was killed that made the universe. What's important is not the similarities. What matters is what's different. The things that the Genesis story tells you that the Babylonian story doesn't tell you. It's the inspired words say, this is what the Babylonians missed out on. First of all, it starts in the beginning, God's already there in the beginning. God's there before there is a creation. God is not a nature God, but a supernatural God. That's new. That's different. That's profound because only something outside of nature can give meaning to nature. A chair only has a purpose because there's somebody who's not the chair sitting in the chair. Wittgenstein said that, only much more elegantly. The second thing is God says at the beginning, let there be light, not because the world starts in a burst of energy, but because everything that's done in creation is done out in the open to be seen. None of it is hidden. None of it is, things man was not meant to know, like the bad science fiction movies put it. Creation occurs in an orderly fashion, as orderly as day follows night. Every step along the way, God says creation is good. The physical universe is good. Chocolate is not some lure of the devil to lure you into acne and obesity. Chocolate is a foretaste of the goodness of God, taken in proper doses. Creation is good. And what's the goal of the creation story? The Babylonian goal was the creation of Babylon. What could be greater than Babylon? The goal, the end point of the Genesis story is the seventh day. It's the Sabbath. It's that moment when we step back, Stop working for food and clothing and admire the universe and its creator. That's the part where we're hungering for more than just food. That's the part where we learn that God made us to be astronomers or philosophers or writers, poets, dancers. It is that sense of we are here to do more than consume. We are here to do more than make sure that we're fed tomorrow. You want to be fed tomorrow so you can do these other things, but we are here to do more than just that. And that is the basis for why we can do science, because the universe does make sense, because things aren't hidden, because it's not overrun with nature gods, because it is good. And therefore, we're not, wallowing around in filth and evil when we're studying the universe.
Thank you.
Brother Guy, another question from Zoom. Do you have any elaborate concept of what time is scientifically or otherwise, other than a sequence of events related to one another and measurable by radioactive decay of cesium in terms of human use? It's an easy question. Take your time.
Yeah, it's a very easy question. No. When I teach freshman physics, I make sure to point out that all of freshman physics can be built on the idea of mass and distance and time. And everybody thinks they know what those things are. And as long as you don't ask yourself too deeply, you'll do just fine. But when you start asking yourself, well, what is distance? It's the measure of what a ruler measures. How does a ruler measure? Because it's got a certain length, which is distance. All of our definitions are circular. Every logical system has to start with axioms, has to start with things you assume. And in Newtonian physics, you have to assume mass and distance and time. Because the longer you try to work out what they are from first principles, the more you realize that I'm in the wrong business and I should be studying metaphysics, not physics. And it's important to remember that logic is marvelous and logic is a creation of God, but it is based on assumptions. And too often we try to prove things, not realizing that all we're proving are the assumptions that we started out with. If you assume the universe has no God, you can look around and see there's no evidence for God because you assumed it wasn't there in the first place. If you assume there is a God, you see evidence of God everywhere. But again, that's because you assumed it was there. That's why we call it faith. When Newton was coming up with his laws of gravity and people wanted him to explain what was gravity, his answer was the same in Latin. He goes, I feign no hypotheses. I have no idea what it is. I can describe how it behaves, but I don't know what it is.
Hello again. You mentioned when you were teaching in Africa, the people were really interested in looking through your telescope and up at the stars. Do you think there's a connection between them living in a place where they are able to see the stars so clearly and wanting to see them even better?
Boy, did I pay you to ask that question? That's a fabulous question. I try to teach high school kids in an online astronomy course. And one of the things I get them to do is to go out and tell me, where was the moon this week? And some of them can't find the moon. We have delaminated ourselves from nature by light pollution, by all the other pollutions. Pope Benedict, giving the homily on Easter Saturday night, when you come into the church with all the candles and talks about light, and that idea that, everything is God. God says, let there be light to show that nothing's in the dark. I swiped that from this homily. He has another place where he says, light pollution is like human sinfulness, where we try to create our own light to blind ourselves to God's light. Most of the light in our cities is useless and wasted and gets in the way of what we don't need really bright lights in our city. Lights that were dim enough so that we can see where we're walking. Our human eyes are good enough that we can then, pick out in dim light where we're going. Bright lights just add glare, it doesn't make things safer. Graffiti is always written in the places in the alleys that are bright, not the alleys that are dark. If you have bright lights, the bad guys can hide in the shadows. And light pollution is one of those frustrating things because it is so wasteful and it is so stupid. And it prevents us from being closer in touch with a universe that's bigger than just me and the refrigerator and what's for lunch.
Thank you.
So the answer to your question is yes.
Brother guys, we begin to wrap up this evening. Before I invite Bishop Persico up here to give us a final blessing, on behalf of Gannon, on behalf of our students, everyone, we want to say thank you for your generosity and spending so much time with us this evening. So thank you.
Thank you. I only wish I could be there in person.
Now, and again, before I invite Bishop Persico up, we of course have one last question for you. Just out of curiosity, would you baptize an extraterrestrial?
Only if she asks. I've got a whole book about it here. It's such a good book, you should all run out and buy 2 copies.
Bishop Persico.
Let us pray. Lord God, creator of the universe, we thank you for graciously giving us the blessings of your guiding presence in the lives of the saints and in the community of the church. May we walk in your light with joy and friendship. We thank you for the gift of this learning community. May Gannon continue to flourish as a Catholic university, a center where students will search for the wisdom that guides their lives and strive to stand by Christ as their teacher. We thank you for the gift of our alumni, friends, and benefactors who have enriched us. Grant them hearts of joy and loving service as they carry out their actions with what they have learned in these halls, and give them the reward of eternal life that you promise to good and faithful servants. Through Christ our Lord. Amen. And may the blessing of Almighty God, the Father, the Son, and the Holy Spirit come upon you and remain with you forever. Amen. Thank you.
For everybody on Zoom and everyone here this evening, thank you. That concludes our program.